Welcome to Tectonic Nights channel. Today's topic is breadth first search. Before we get started, make sure to subscribe so you don't miss out on more content like this. And do check out my GitHub repository where you can find all the coding solutions we cover in the video. Now let's get into the BFS section. First problem is Univalued binary tree. In this problem, we need to determine if all the nodes in the binary tree have the same value. If they do, we return true, otherwise we return false. Let's start coding. So for BFS, we need to traverse level by level. Let's start by creating a list named queue and initiate it with root node. We start by popping the front of the queue, which becomes the current node. Then we add the left and right children of this node to the queue if they exist. This is for the first level. To process each level of the tree, we continue this in a loop until the queue is empty. Now when we run this, we get this error as we are trying to access non-existent nodes. Let's add a condition to check if the node has a left or right node. Finally, let's add a condition to break the loop when the current node's value doesn't match the Univalue. This is the basic template for BFS. Now let's practice this on other problems. Next problem is to return a list of lonely nodes in a binary tree. A lonely node is a node that has only one child, meaning either its left or right child is missing. We start with a queue containing the root node. Then for each node in the queue, we check if a node has a left child. Then we enqueue that left child. Similarly, if it has a right child, we enqueue that right child. As we enqueue, we also check whether it is a lonely node. When we enqueue the left child, we check if the right child exists. If it doesn't, we add the left child to the lonely list. Similarly, for the right child, we check if the left child node exists, and if it doesn't, we add this right child node to the lonely list. Next problem is find a corresponding node of a binary tree in a clone of that tree. We are given a target node from an original binary tree, and we need to find the corresponding node in a cloned version of the tree. Here's an example. This is the target node. Here's the corresponding node in the cloned tree. We start by performing BFS on the cloned tree and check each node to see if it matches the target node's value. Now the follow-up question is that, what if there are duplicate values? In our previous implementation, we checked if a node's value matched the target node's value. However, this approach doesn't work when there are duplicate values. For example, suppose the target is the left node of the original tree, which has a value 3. The original tree's right child also has a value 3. When traversing the tree row by row, we will encounter the right child first. Since its value matches the target, our previous method would mistakenly return the right child's corresponding node in the cloned tree. To fix this, we'll traverse both the original and the cloned tree simultaneously. We can achieve this by initializing two queues, one for original tree and one for the cloned tree, and process them in parallel. As we traverse, we'll check not just for a value match, but also for a reference match. Next problem is cousins in a binary tree. Given two node values, we need to check if these nodes are cousins in a binary tree. Let's define a function that is used for traversing a binary tree until we find the target. Note that we need additional information, not just node's value. We may need the parent node information as well. Let's update our queue initialization to include the parent node. We'll set it to none for the root node. Now, as we process the node, we pop the front tuple, which is the current node and its parent. We append the left and right children to the queue and current node as the parent. Let's execute this cell and pass one of the targets given in the example, say 5. We can see that it returns the matched node and its parent's value, which is 3. Now, in order to determine two nodes are cousins, we not only need their parent nodes, but also the level or depth information. Let's update the queue initialization with the level info. For the root node, it's 0. We append the left and right children of a node, each with an incremented level value. Let's modify the function to check both the targets simultaneously by adding two parameters x and y. As we traverse the tree, when the current node matches x, we store its parent and level information. Similarly, when the current node matches y, we store its parent and level information. If we recorded both parent x and parent y, it means we have found both the target nodes. At this point, we need to return the relevant information that will help us determine if two nodes are cousins. Finally, we check whether the levels of the two nodes are same, whether their parent nodes are different. In this case, x and y are cousins. Today's final problem is an introduction to BFS in graphs. We are given a list of bidirectional edges represented as a 2D array of integers. Each edge connects two nodes. The task is to determine whether there exists a valid path from a given source node to a destination node in the graph. Here's an example graph. We will begin by initializing the queue with the source node as usual. Next, we use our BFS template. Instead of checking just the left and right children, we iterate through the neighbors list of the current node. For each neighbor, we append it to the queue. Since the graph has bidirectional edges, we may encounter repetitions, and we might not be able to exit the loop if we keep processing the visited neighbors. To handle this, we initialize a visited set and add the source node to it. Note that we use set instead of list here, as this is much faster than using a list. When checking membership, set would take O of 1 time, whereas list would take O of n in the worst case. As we iterate through each neighbor, we check if neighbor is already in the visited set. If it is, we skip appending that neighbor to the queue. Finally, we need to check if we have reached a destination. If the current node matches the destination value, we can exit the loop. Thanks for watching the video. I hope you enjoyed it. See you next time.